So the rest of chapter 12 is analyzing bivariate data, which is just fancy for having our X and Y list. It throws us back to chapter 3 with all things regression, a confidence interval and a hypothesis test just for the slope. We're not analyzing the y-intercept. And these are just a few of the objectives. So checking the conditions, of course, construct and interpret the test, and then computer output comes back and is very important. So in chapter 3, whenever we were describing a scatter plot, we talked about form, strength, and direction. So not the same SOCs as when we were describing histograms and dot plots. R was our measure of linear association, and so that really should match direction because it's positive or negative, and the strength can be balanced on that. R squared, remember, is the idea that we are using our regression model to explain the changes that we see happening in the y variable, and how much better is it than using just the mean model if that was the best that we could do. So our model, our least squares regression line, remember that's what RL stands for, always has to be y hat, so we know it's not algebraically a line where all of the points fit. And the residuals, remember, fun facts, that they always have a sum of 0, so they have a mean of 0. Whenever you do lin reg on the calculator, it's actually finding the least squares regression line that automatically generates the residual list for you. So what we're dealing with is what is the truth about the population. So the true regression line, and in the population, how much do we predict the change in y for every one increase of a unit in x. And remember that that is always how we interpret it, the slope, that it's always about the predicted amount. And measuring margin of error again, how much do we expect that to vary? And then is there really a linear relationship, or could it just be due to chance, which is what we were always answering with our test. So sampling distributions, because we have to know if we were to take all possible samples of this particular size, what's going on. So we have A plus BX. A and B are unbiased estimators. Those are my statistics of my parameters, which would be alpha and beta. So that's my true intercept and true slope, and my true mean response, mu sub y, having that straight line relationship. So basically replacing the y hat with the mu sub y, and then A and B are replaced with alpha and beta. So this is the highlight for today, checking the conditions. We use the acronym LINER to try to remember them all. Linear is pretty easy. We should get a pretty good idea from the scatter plot. We can also check the residual plot. So that's something we know how to do. Independent is something we also know how to do. Nothing has changed there. Normal we know how to do, we just haven't done it. So the one that you have to watch for this, with the data, if you were then able to input the data into the calculator so you can run linreg, you'll get that list of residuals, and this is what we're looking for. So we want that list of residuals, a stem plot you're not going to make on your calculator, but you can check a histogram, you can check the normal probability plot, which is that last stat option, or you could even check with a box plot to see if there are any outliers or other major departures from normality to see if those residuals are approximately normal. And then equal variance, the scatter in my residual plot that I could have checked back when I checked the linear condition, should be about the same across the board. So from the smallest to the largest X values, so from left to right, they should be pretty evenly scattered. I don't want to see early on for small values that my line is predicting very well, that the points are very close to the line, which is what the residual is measuring. So those would be small residuals, and then have it kind of fan out at the end, that it's getting less accurate for larger values of X. And then random, we also already know from the context. So linear, having the scatter plot, the residual plot you could look at, and then that would also help with equal variance. And then normal, you need a second plot there. So you could potentially have sketches of 3 different plots to check those conditions. And then independent and random come from the context. So often, all of that work is already done for you. And then you just have to confirm that it is in fact correct, that everything has been checked, that we don't have any violations, and don't have to say proceed with caution before we move on. And they are exactly the same for the confidence interval as they are for the hypothesis test. So this is just a visual from the book to see, if you think that population lines, you can see in the bottom left corner the mu sub y, and then at some point on the line checking each of those residuals, or checking the residuals at each of those x values to see that they do vary according to a normal curve. And like always, the smaller the standard deviation, the closer the points are to the line, and the larger, the more widely spread it will be. So once we do this, then the slope is an unbiased estimator of the population slope. And again, standard deviation describing that variability. So it is connected when we think with correlation. This formula is not one that you really ever have to work with. It's the interpretation, though, that you need to know. So since we don't know sigma, we would never know that much about the population. We have the standard deviation of the residuals S, and then we can use that to find in our sampling distribution the standard error of the slope, which again, you don't often have to calculate either of these. They're usually given to you. It's more so the interpretation. So recognizing for standard deviation, it's how much they vary from the line, and recognizing with standard error that it's how much each of those slopes vary from what the true slope would be in my sampling distribution. If we, and this is just to show where one of the formulas come from, transform all of those different slopes, because again, remember that when we're trying to look at our sampling distribution, it would be every possible slope that we would find from samples of that particular size. Looking at the z-scores, we end up with a normal distribution, but since we don't know what sigma is, when we replace it with its standard error, this gives us a test statistic. And then degrees of freedom, instead of n-1, like what we were used to back in the early chapters, is now n-2. And I always just think we have two variables now. We have the x and the y. And then that test statistic is really what we're using for our hypothesis test. So before we get there, and this is all done for us, your computer output, and this was from a different example based on seating location, but remember that coefficient column is my A and B, and so the y-intercept is the 85.706, the slope is negative 1.1171. What we haven't worked with yet is that the standard error is right next to it. And so if you would take the slope and divide by the standard error of 0.9472, that gives us the negative 1.18, which is the test statistic that we saw. And then the p-value is there without me having to go to table B to find it. S is that standard deviation of the residuals again. R squared we could convert into a decimal point and square root to get R. That would be easy enough. And so the regression line is shown below. That should be a score with a little hat over it. And then A plus BX. And since my slope is negative, that's just that negative value. So then a couple of notes here. We never do anything with the y-intercept. It's just really not statistically all that useful to analyze. And then again, know that what we're expecting to happen is how we interpret the slope, and it's estimating that value beta. And then same thing with standard deviation, so a typical prediction error, what would happen. And then test statistic and p-value is what we'll finish up with the hypothesis test. So here is just a sneak peek what the confidence interval looks like. It is still in the form of estimate plus or minus margin of error. So B is our estimate for beta, and then margin of error is the critical value multiplied by the standard error, and we're back to T star for our critical value, and then standard error is abbreviated as SE sub B. My hypothesis, my slope is typically 0 because it would be a horizontal line that has then really no relationship. As X is changing, I'm not seeing any change in Y. And so B minus that beta sub 0 divided by the standard error of B. And then again, the p-value we get just from using table B. So the highlight again are the conditions They are exactly the same for the confidence interval and test. And then just a few adjustments talking about now sampling distribution for slope, reminders of things from chapter 3 in that computer output. And then this should help for us to work through a confidence interval and test problem.